Okay, so what we're going to do today is we're going to finish the final that we started last time. Once again, well, not once again. Welcome to the last Physics 213 lecture of the semester. Next, there will be a review for the final tomorrow, 1 o'clock to 3 in Bishop's main lecture hall. If anybody is in there, it's our room, so you can kick them out. We got as far as problem 3. Oop, bump it with my head, not good. So we got it through problem 3. Problem 4 is a two-dimensional motion problem. All right, there we go. You will have a two-dimensional motion problem on the final. So let's go do this. Now for all these problems on 2D, they will end up, I'm not going to give you a problem that's silly and it'll go up and down like that and won't make the ledge. So in this case, it does make the ledge, and I believe that during the final I told them that. Determine the initial velocity of the ball and the angle of the hit given the conditions listed below. Horizontal distance 200, vertical distance 40, time of flight 10. Give me the initial velocity and the angle. This is a classic two-dimensional motion problem. X equals x naught plus v naught xt plus 1/2 at squared. Actually, you don't need the a because there's no horizontal acceleration. Next, y equals y naught v naught y t. That y should be a subscript. Now, with this type of two-dimensional motion, the best way is to pick the origin at the launch point. Up is positive, right is positive. X naught and y naught are both 0. This is a standard launch. V naught y, v naught sine theta, and v naught x, v naught cosine theta, or v naught. So x is v naught t cosine theta, y equals v naught t sine theta plus 1/2 at squared. As with everything above marked is an unknown, everything marked below is a known. X, t are knowns, v naught and theta are the unknowns. We're dealing with an acceleration that's down, that's negative g, so a is negative 10 meters per second squared. Standard 2 equation 2 unknown. Best thing to do, solve for t. I'm sorry, best thing to solve for v naught. X over t cosine theta, y equals v naught, or x over t cosine theta, t sine theta, plus 1/2 at squared. T's cancel, left with y, x tan theta, plus 1/2 at squared. Everything is a known quantity except for theta. Solve for theta. Y minus 1/2 at squared is equal to x tan theta. y minus 1/2 at squared over x is equal to tan theta. Theta is the inverse tan of y minus 1/2 at squared over x. And there we go. That's the equation. So, excuse me? X equals V naught T cosine. Oh. Well, X is V naught XT. V naught X is V naught cosine theta. So the T comes down, the V naught cosine theta comes down as well. All right, you're welcome. So this becomes inverse tan of y 40 minus 1/2 negative 10 squared over x 200. Negative negative is positive. That's a 5. 5 times 100 is 500. So this is inverse tan of 240 over 200. .2 degrees. So that's the angle. 8 squared for the time. Time is 10. We are looking at the summer of 16. Actually, what am I looking at? I thought this was the right one. Larry version. May have. Hold on. This is the type of problem that we were looking at it? All right, okay, I may have had the versions switched up. So, this is for the Mo. Okay, fine, I had something stapled onto it. So, with that being 10 seconds, doesn't change the solution or the algebra at all. So V naught is x 200 over t. In this case, we're going to use the Mo version. Or actually, don't care. Cosine 50.2. So that's 20 divided by the cosine of 50.2. .2 meters per second. So for the Mo version, it's 50.2 and this. The only thing that's different with the Larry version is that it's 8 seconds. So fine, you put 8 there and 8 there, and then you just propagate the numbers through. The solution itself is still correct, just the numbers. All right, I'm gonna start with the Larry. Tell me what the Larry version is for problem 5. A tuning fork. The one that I have says 210. What does 200? All right, we're gonna use the Larry version. The tuning fork has a frequency of 200. L is still 1.4, right? Yes. Okay. L 1.4 meters. It is the lab. You've got the water jug. The water falls. How many resonances are there and at what levels are there? So if you use that as 0, at what values does this thing resonate? We're going to use a velocity of sound as 350. This is a half pipe because the water's blocking the other end. And to make the one student happy, I think Sabrina, take out a sheet of paper. You take out a sheet of paper, put your name, today's date, student ID. Sabrina, do the same thing. Adrian, take out a sheet of paper, put your name, student ID on it, pass it around, make sure everybody signs before the end of the lecture. Congratulations. If you're going to be here at the last lecture for 213, you're rewarded. Bad people online. If you want to clap, yay. All right. Thank you, thank you. You're too kind. It's not as good as There's No Friction, but it's good enough. All right. I'm going to stop and talk about something else. All right, now for the frequency. NV over 4L, where N is 1, 3, 5, etc. Really all you're looking for is the length is V over 4F. That means that the first resonance is 350 over 4 times 200. 350 divided by 800 means 0.4375. Now for the third resonance, it's 3V over 4F, 3 times 350 over 4 times 200. And I think that makes it even still to, oh wait, no, it'll work. 1.3125. If you put a 5 there, you would get a number that's bigger than 1.4, which means that that harmonic is impossible. So the answer, there are only 2 lengths where this will work, 0.4375 and 1.3125. And you can round, that's fine. Probably to the nearest centimeter. And so that's problem 5. And the other thing that I'm really interested, yes?
Why did you say 5 would work as the gradient?
Well, let's do it. If we used n equals 5, 5 times 350, 4 times 200, what number do I get for that? A big number. Divided by 3 times 5. I get 2.2. The length of the experiment is only 1.4. So it can't happen at 2.2 because that's physically impossible. Okay, Larry's version still has Fish of Fury as problem 6, correct? Adrian? Fish of Fury for problem 6? 120 meters, okay. Okay. So the Rebel rod and reel has 120 meters of fishing line on the spool. You cast 12 meters out. The whole length is 120, which means that the length that it moves is 108. Spool has a radius of 4 centimeters. The velocity of the fish is 12 meters per second and constant. If it is constant, A is equal to 0. Now the first question is, how long would it take before it runs out of line? x equals x naught plus v naught t. I'm not worried about 1/2 at squared because a is 0. So x minus x naught is equal to v naught t. X minus x naught divided by v naught is equal to t. X is 120. X naught is 12, or 108, divided by 12. A lot of 12s wandering around. 9 seconds. That's how long it would take before the spool runs out. How many revolutions did the spool make when it runs out of line? Well, if you know the circumference, which is 2 pi r, and you know the number of rotations, you've got the distance. If it rotates 1 time, and let's say its circumference was 1 meter, if it rotated 10 times, it would have rotated out 10 meters of string. So this d is distance. Now the distance is the 108 because you already have 12 meters rolled out. So the distance divided by 2 pi r is equal to n, or 108 divided by 2 pi, 0.04. Or 429.7. I'd accept 430 to the nearest rotation. So it made 429.7 revolutions. Now I need to also know period, frequency, and angular acceleration. Now since some of you were here in the morning, if you call out what the answer is, just don't do that. Only people who are here in the afternoon. Which one of the following 3, period, frequency, or angular acceleration, is trivial? What is that answer and why?
Alpha. It's 0.
Why? Because?
Because you put the 1 0 on the bid. So this is gonna be 0.
Right on the first half, incomplete answer on the second. That's philosophy. That's across the circle.
It's a constant velocity, so the acceleration has to be 0. It's never changing. It's rotating.
Radial acceleration is 0.
Right.
Or I'm sorry, radial acceleration is not 0.
It's rotational velocity.
What's the equation that makes that association? Or what equations do you need? V is omega r. If V is constant, omega must be constant as well. And what is d omega dt? Alpha. So if omega is constant, the change in omega is 0, therefore alpha is 0. So it made 429 revolutions in 9 seconds. So the frequency, you could say, is the number of oscillations per total time. 429.7, total time 9. .7 hertz. The period, which is inverse frequency, gives it 2.10 times 10 to the negative 2 seconds. And that's problem 6, and that is the end of the Larry version of Summer 16. Summer 16 final. Yes. Can we assume that there will be a trivial question on the final? Perhaps. I mean, yeah. Yeah, I mean, there's some multiple choice. In a problem? Could be. I mean, there was, yeah, maybe. I don't want to tip my hand, but yeah, it'll be an intentional, you're trying to box me in and get me to say I'm going to try to trick you. My response to that is I'm going to give you a question somewhere in the test where you're going to go, oh, how dare you? It's obvious that it's this, and then just move on. Yes?
This is the problem where alpha equals 0, where on the test it did equal 0, right?
Correct. And the big difference that you can tell between the two, there was no external force. Yes?
I was just going to ask to confirm we're getting a Fisher theory type problem on the final.
If we're gonna get it, I can neither confirm nor deny. And am I telling you the truth or am I lying? Or am I lying about lying? I don't know. So, honestly, I haven't written the final yet. Final won't be written until over the weekend. Had I written the final and told you this, you would have me just tied up until I gave you the final. So I just wait until I'm in a safe location and then I write it. So, any other questions? I mean, once again, let's review all the tests that I've given you before. There's not a single problem that we've not talked about. Now, granted, if any of you say I've taught you A plus B equals C and you're offended that I give you A and C and ask you for B, well, that's your problem. That's algebra. This is all about problem solving. Any other questions? All right, we're going to talk briefly about also what I've done. Well, I've tried to work on the multiple choice. About 40 students of my wonderful students have come by asking questions. I haven't gotten squat done. But this is the summer 15 final. As you can see, there's some similarities. We did this in the morning. We've done this. We've done something like that. This was on test 3. I think we've done something like that before. No, we haven't done something like that before. We did it in the other class. And then on page 2, we did this, and we did this, and in the AM class, we did this. Given these distances, that frequency of the string, this was the hybrid problem. Given all these factors, what was the mass hanging at the end of the bar? That problem was done in the morning and it's currently available on YouTube. So this is,
Which test is this?
This is something that they just asked me to sling together. In fact, it's similar to the last problem on problem set 11. And remember that the last problem on problem set 11 I eliminated. It was the one where this was dunked in water, but this is the one where there wasn't water. And so I did the whole thing in great detail, and so you can just take a look at it. figure it out. But if you see anything that we haven't done in the morning, and don't worry, we're gonna get credit for showing up and we're gonna leave early. If you want to talk about this, or you want to talk about other problems, I'm game. If we work here for another 20, 30 minutes, that would be fine with me. So, yes.
That number 2 problem, not this. Where it shoots.
Oh, this one?
Yeah.
Okay.
That one.
All right, this is number 2, Sigma version. This is the final from summer of 15. This is like the lab. You have a ball coming to hit another ball. They stick. The arm is massless. I give you the length. They go up a particular angle. I give you all the masses. What is the velocity of the ball that made impact with the second ball? So there are 2 problems. From a geometric point of view, it rose a height h. This is not to scale. If that is length L, that is length L, which means that this length is L minus h. Cosine of theta is the adjacent side, L minus h, divided by L, solve for h. L cosine theta, L minus h. H is equal to L minus L cosine theta. And so L1 minus cosine theta. And so that is an expression for the height as a function of the length L and theta. Now, this is a conservation of energy problem. There's no friction, there's no collision. This is post-collision. So the energy at the B state is the same as the energy at the C state, excuse me. Here, it's entirely kinetic. There, it's entirely potential. The kinetic, 1/2 combined mass, V squared equals mgh. This is the combined mass. I don't really care about the combined mass because they cancel out anyway. This leaves you with V squared over 2 is equal to GL 1 minus cosine theta. Now, what I'm going to look for is V squared is equal to 2GL 1 minus cosine theta V 2GL 1 minus cosine theta. And so you could find a number for that, so whatever. But I'm interested in the algebraic notation. This is the velocity, the combined velocity of the ball and the arm, mass, whatever, at the point of B, immediately after impact. The impact is conservation of momentum. The momentum at A is equal to the momentum at B. The momentum at A is only m1, v1. v2 is 0, so you don't really mention that. Momentum at B is m1 plus m2 times, and I don't have enough space, so I'm going to kind of draw it down here. 2gl 1 minus cos theta. Now what am I looking for? I'm looking for v1, the velocity of the ball initially. This is m1 plus m2 over m1 2gl 1 minus cosine theta. And that is the answer for velocity. Plug it in. M1, 1, M2, 5, M1, 1, 2 times 10 times 0.4, 1 minus cosine 40. And so that's it. 20 times 0.4 times 1 minus cosine 40 square root times 6. 8.21. And that is the velocity of the ball. That's the velocity of the ball before it hit the arm which was at rest, which then later rose up to 40 degrees. And that is problem 2. Yes?
How do I know that there was a velocity before the ball?
How do I know that it's the velocity of the ball that what?
Like you said there was a velocity before the ball hit?
The object was moving at a velocity of 8.21 before impact. What we did is we worked backwards. We worked from the fact that it rose to 40 degrees, which means it lifted a particular height. So that height implies a potential energy, which then implies that the masses were moving the moment after impact. What was that velocity? This. Then we realized that it is an inelastic collision. The momentums have to be equal. And then we solve for it. Which is really, if I wanted to do m1 v1 is equal to m1 plus m2 velocity combined at B. And that's the velocity combined at B. All right. Sigma version, summer of 15. I mean, this one's Doppler shift. That's the roulette wheel problem. This was done. Any other questions? Or what's the next question? Yes?
Would you do a problem where it's done in the water on the final?
Would I, like right now or on the test?
Or on the test?
Hold on. What was the question again?
Whatever you dump it in water, I was wondering if you would put a problem like that on
You mean like
the last problem we did before this.
on the last problem before we did this?
The bar with the mass hanging off of it and the string. And then
Oh, you're talking about that which I outlined. You're talking about this.
Yeah.
I'll tell you what I told the morning class. No. So I'll make that clear. That's enough of a hybrid problem. If I put it in water, I would then turn it into a 30-point question rather than a 15. So let's not. You know what? Let's not. So, yes.
Are we gonna have another question, sort of like on our test 3? Like,
Another question, sort of like what we did on test 3. Oh, the hole in my bucket. I would say that you do, if it's not, it won't be the bucket, but I'll say this. You've got to know Bernoulli's equation. You've got to know equation of continuity. You've got to know that volume is the area times velocity times time. And you got to know how to manipulate those. Those definitely will be used. The bucket problem was interesting, but I got other stuff to do with that. If you notice, like when we went over on Tuesday, the big problems, take a look at the Tuesday lecture for a refresher. Atwood's machine, vector addition, 2D motion, circular motion. There was, collision. So that's 5. 5 non-test 3 problems, which means there's only going to be one problem, and most likely the 2 appetizers would be test 3 stuff. So I only got one shot to test 3 material, and those appetizers most likely will be small and something that I can do with test 3 stuff. I mean, this is a collision problem. Just remembering collision, conservation of momentum only. Yes. Are we gonna what? Yes, of course. Did I not say that? I did, yes. Okay. Now you're making me wonder about my sanity. Next question. Multiple choice. I'm going to go over it again, kind of proof it. And one of the things that I would like to do, or I mean, just as an example of stuff that I'm going to try to put in a little bit more. Radial acceleration, you increase velocity, what happens to radial acceleration? Radial acceleration, you increase the velocity of the point at the edge. Does radial acceleration increase or decrease? So you've got a wheel. Wheel spins faster. Is the radial acceleration increasing or decreasing? Well, it's v squared over r. Let's figure it out. Now you're making me doubt myself. But disagreement. So AR is v squared over r. And so when I do this and then spin around faster, that means omega increases. So v is equal to omega r. This means that v squared is omega squared r squared over r, which is omega squared r. So in radial acceleration, if I cause the thing to rotate more quickly, yes, the radial acceleration would get bigger. This is the different question, because there's the other question. You're on a spinning disk. You move further away. Does your radial acceleration increase or decrease? Most people say decrease because radius is in the denominator. But when you substitute for v, it becomes directly proportional to radius. So if you increase v, you increase AR. If you increase R, you still increase radial acceleration. So I really enjoy that increase this, what happens to this? Decrease that, what happens to that? Those relationship ones. They're really good on multiple choice. So, next. We got 19 minutes to kill. We're gonna stop at 5, for sure.
Are you gonna post the answers to the multiple choice?
I am gonna post the answers to the multiple choice. I will, if I can get around to it. So many of my wonderful students have been visiting me with 89.4 on their lab their lab grades and wanting to know if I'm gonna round up.
Is that shady?
That is shady.
Oh, okay.
So that's why I was salty.
Okay.
So, so it was, that was, so that was it. So this is also, just to put it in comparison, 30% of 3 units is roughly 0.9 of a unit. So the final alone is worth 90% of your lab score, equivalently. So if you, let's say I'm generous and give you an A for the lab, but you leave a crater behind on your final, it doesn't matter. Because, I mean, your class grade just goes boom. So, huh?
Your class grade affects your lab.
No. I'm just saying comparatively. If you compare, what's 30% of a 3-unit course?
Okay.
0.9 unit. What's your lab? 1 unit. So they're equivalent, effectively. I mean, other questions? What's on the final? You don't have a question? Or,
Like technically, so if you would get the B in lab instead of the A, and you still do terrible in the final, then that's why you want the A in lab.
any other questions? Aside from pointless observations. Any other stuff? I'm trying to think what else. Atwoods. Oh, the one thing that I will say that alpha equals 0. More importantly, this means no external forces, no torque. What is allowed, so Fisher Fury, also conservation of angular momentum L. The other thing, and this is where most likely this little bit will come in, it is metaphysically certain, I would almost say, calculate moment of inertia of object parallel axis theorem is required. So you're going to use the parallel axis theorem for sure, which basically means you're going to have a stick, or if I was really mean, a cylinder that'll be rotating off of its center of mass. Most likely a stick. So they're not going to be as nice as as this. So you're gonna have to know about how to use this, where that is the distance from rotation point to its center of mass.
Is that always L divided by 2 or not necessarily?
Is that always what?
L divided by 2 or
Not always. I mean, you're gonna have to look at it and figure it out. I mean, as an example, just to calculate D, let's say the radius of the disk was 2 meters, and this length was, well, in this case, it's 4. No. Oh, I know what I'm trying to tell you. A lot of people would say, well, D is just the radius of the disk. But instead, for this case, if the stick is fixed at its end, then yes, it would be L over 2. But let's say I did this. The radius was 2. That means I've got 2 there, 2 there, and definitely not to scale. 1 there. So let's draw this again. Stick length is still 5. Which means its center of mass is somewhere in here. So if that distance is, let's say, I need a bigger. Two, 2, 1. The center of mass is still at 2.5. So that's 2.5. This is 2.5. So that distance right there is 0.5. I'm kind of looking at there to there. I know that the center of mass is 2.5 meters from this end. It's also 2.5 meters from that end. But that length is 2, which means this length is 2.5 minus 2, or 0.5. So it's not always L over 2. So you're just going to have to reason it out. Problem solving. Yes. Next question. So parallel axis theorem. Gotta know it. Could be worse. This could be the Cal-based physics course. We'd have so much fun in that one.
I didn't know that 2.5. Like, I don't.
Because it's a 5-meter stick. If I said, so this stick is 5 meters, which means 2.5 and 2.5. The circle is 4 meters across. So from there to there, that's the diameter, which is 4. Now, center of mass for a 4-meter region is 2. So if this is 2, and that's 2.5, while this is 5, that difference is only 0.5 meters. All right, 9 minutes. Your prisoner's here for 9 more minutes, and then we can go.
Can you do it up here on the SSD on the top?
Oh. What I'll do is, no, hold on. So you have a disk with 2 masses. Each mass of the point is 10 kilograms. The mass of the disk is 50 kilograms. Let's do something like this. Or let's make it easier. The radius is 2. And then this stick is 20. meters, which means that the distance to its center of mass of the stick is 10 meters. So 0, 2, 4, and then 10 and 20, not to scale. So this distance here is 8 meters. The distance from the center of mass of the stick to the center of rotation. What is the moment of inertia? Total. The total moment of inertia is the moment of inertia of the disk plus 2 times the moment of inertia of the point particle, plus moment of inertia of the stick plus mass of the stick d squared. That part is the parallel axis theorem. Now, like the masses, if you got 2 5-kilogram masses, how much mass do you have? 5 plus 5 is 10. Add them together. Moments of inertia, you just add them. Moment of inertia of the disk, 1/2 m disk r disk squared, plus 2 times point particle moment of inertia. Mass of the point, radius of the disk squared. That's because the point is at the edge of the disk. The moment of inertia of a stick, 1/12 ml squared. That's mass of the stick, plus mass of the stick, d squared. D in this case will be 8. So 1/2, 50, 2 squared, plus 2 times 10 times 2 squared, plus 1/12. Oh, I didn't give a mass of the stick. Mass of the stick, 10. Its length, 20. Mass of the stick again, 10. D, 8 squared. Four divided by 2 is 2 times 50, 100. 20 times 4 is 40, so 140. Now it gets complex. I get 1113 1/3 kilograms meters squared. And one of the things that we need to remember, I use these review sessions as ways to sit there and go, if I gave him this problem, how well would it go? This problem would probably go badly. But if I gave you something like this, let me think about a hypothetical problem. If that's the center of mass, let me simplify it just a little bit. Okay. So the stick is rotating about that point. Let me ask you a dumb question. What's the length of the stick? 10. Great. Good start. What is the length of B? 5. Why is it 5? It's a half. It's at the center of mass, which is typically half. If it was Cal-based physics, it wouldn't always be at the center. So if B is 5, and I made the rotation point 3 from the other end, 2 is A. So in my parallel axis theorem equation, which is this, what is the value of L that's being used in that equation? 10. Excellent. What is the value of D that's being used in that equation? 2. There you go. So one thing I've learned is complex geometries we're still not ready for. Something simple like this looks like a very good appetizer problem or multiple choice. Yes, that's the definition of the D, the capital D that's used in the parallel axis. Is it 5 o'clock? I think it's 5 o'clock somewhere. Close enough. If we round up, it's 5 o'clock. Yeah. Okay. All right. Class is over. See you tomorrow.